Hello students, welcome back for the class. Our today's topic is inverting Schmitt trigger circuit. Okay, inverting Schmitt trigger circuit. We call it a Schmitt trigger because this particular circuit will get triggered at two different reference voltages. That is, the positive reference voltage we call it as UTP, upper threshold potential, and the lower reference potential is LTP, lower threshold potential. Okay, so this UTP and LTP will be acting as the reference voltage for your inverting Schmitt trigger circuit to change its output from positive V naught sat to minus V naught sat and minus V naught sat to positive V naught sat. Okay, and the circuit for doing this is this. So the input is applied to input is here, output is here. Okay, suppose we have given this as your input. Okay, this as your input, that is sinusoidal input waveform. So this sinusoidal waveform, let me redraw it here. All right, this will continue. This will continue like this. Now, if you see here, the input for the circuit, this is your input, sinusoidal input. Its amplitude is more than UTP, isn't it? See here. Well, now this particular circuit, when you apply this input with the help of resistance R1, which is connected in feedback, which feedback is used here? Positive feedback. Just concentrate here, plus sign. So far you have seen negative feedback, but here we will be using positive feedback. Rest all things are as it is. VCC minus VE all will remain same. So this will produce the output. How it will produce? Input is given to inverting terminal. So positive input will produce negative output and negative input will produce positive output. All right. Now, so as I said, we have seen zero crossing detector, right, and a comparator circuit, right? Zero crossing detector and voltage comparator, both circuits we have seen before this topic, right? So considering both those topics, you need to understand this. So your output, let me draw with red pen. This is the instant where your output switches, this instant. See? All right. So your input before crossing this UTP at this instant, suppose you are here, say I am increasing, your input is here below UTP. When your input is below UTP line, your output will remain positive. This is V naught sat line, positive voltage line. This is negative voltage line. All right. So the moment your input crosses this UTP line, whenever it crosses UTP or when it reaches UTP, your output will shift from positive to negative like this. Your output will shift like this. It will shift and it will go for negative saturation level. When it will change, the moment your input crosses UTP, your output which was positive will come to negative saturation level. Okay. How long it will remain in negative saturation level? It will remain in negative saturation level until your input goes negative, negative, how negative? More than LTP, or when it reaches LTP at this instant. When your LTP should negatively increase till LTP, then your output will shift and goes to positive and goes to positive saturation. Understanding? Now how long it will remain positive? Until your input is below UTP. Until your input is below UTP. See, till here it is below UTP. The moment you reach here, your input reaches UTP. So your output will shift once again like this and goes to minus V naught sat. This is how it continues. So you will be getting a rectangular waveform like this, and the triggering is taking place at UTP line and LTP line. UTP line and LTP line. For example, this UTP can be plus 2 volt here, here minus 2 volt. Understood? So whenever input is reaching plus 2 volt, your output will change, and here whenever input is reaching minus 2 volt, your output will change. Now this is inverting Schmitt trigger. Inverting because we have you can see your output. When your input is positive, your output is negative. When your input is negative, your output is positive, because input is applied to inverting terminal. Same thing, same input if we apply for non-inverting terminal, this will give you positive output with positive input, okay, and negative output for negative input. These things you already know, right? So let us see its design. This is our zero line, okay, zero line. So no need to write voltage here. It can be any voltage more than 0, plus 1, 2, 3, 4, anything. All right. Let us see its design now. Now we require to find resistance R1 and resistance R2, right? Now for this, the voltage at non-inverting terminal is given as, yes, tell me, this point. So let us call this as VR2, isn't it? This is our VR2, right? How can we write VR2 voltage? What is the opposite voltage at this point? This voltage is nothing but this voltage, isn't it? What is the opposite voltage? V0. The opposite voltage for this node is V0 in the other branch. What is the resistance for VR2 voltage? It is R2 to R2 divided by sum of the resistances. We have resistance R2 and R1. So I will write R1 plus R2. Hope it's clear. Now now you understood what is VR2, right? Now this VR2, in our previous circuit of voltage comparator, we have seen VR2 is working as a reference voltage which will decide when the output will switch from one state to the other state, right? So let me call, if our VR2 is positive, then it is UTP. Concentrate here. VR2 voltage, this VR2 voltage is acting as our reference voltage here. So we call VR2 equal to UTP when your VR2 is positive. Okay, if VR2 voltage is negative, then it is LTP. Let me write here. When the output voltage is saturated in positive direction, that is plus V naught sat VR2 is a positive voltage, a positive quantity. It is known as UTP, upper threshold potential. It is called as UTP. Therefore, we can write UTP is nothing but our VR2 only. So I can write V0. Which V0 I should use now? Positive V0 sat. It is not just V0, it is positive voltage. Then only it is UTP. Okay. Rest all things will remain as it is. R1 plus R2. This is how you will be getting your UTP, and if UTP is given, you can get R2. Alright. Next, same statement, when output voltage is saturated in negative direction, then that is minus V0 sat, then VR2 is a negative quantity, it is known as LTP. So I can write LTP as minus V0 sat into R2 divided by R1 plus R2. What is changing here? Only the direction of output voltage. Alright. Now, let me write design for this. How will you get resistance R2? Just see the circuit. Resistance R2, how will you get? The voltage across this is VR2, right? The voltage this is across, this is VR2. This VR2 is also called as trigger voltage. VR2 is called as trigger voltage. What VR2 is also called as? UTP and LTP, right? VR2, this voltage is also called as UTP and LTP. What are your UTP and your LTP? They are triggering voltages. So we also give a name for that. Trigger voltage. Trigger voltage divided by current I1, I2, anything can be taken. We know what is the current flowing in op-amp circuit, right? It is always 100 times of IB max, right? So this is your R2 value. How will you get R1? This voltage is this voltage minus this voltage, right? Your output voltage minus reference voltage. Output voltage minus trigger voltage divided by current, same current. Clear? Now, if you are using a bi FET op amp, see, all this design is when you are using 741 op amp. Okay, when you are using 741 op amp, most of the time you will be using 741 op amp only. Very rarely you may get a question to solve by using a bi FET op amp. In that case, you need to assume resistance R1 value as 1 mega ohm. Okay, 1 mega ohm. Well, now this is your design equations. Now one important part is left out, that is input output characteristics. Input output characteristics for this circuit diagram, this waveform, and that characteristics I need to plot. Let me clean the lower portion of the board. Yes, I have cleaned it. So this is your circuit. So we require to understand input output characteristics. Input output characteristics, very important part of this topic. This characteristics plays very important role in this particular topic. In your particular in your video question paper, in video question he will specifically ask, along with this topic, explain input output characteristics. Okay, so all of you need to concentrate here. So let this be your V in. Okay, this is your minus V in, positive direction, negative direction, input, and let this be your output. V naught, positive V naught, negative V naught here. Okay, now how much your output will increase? So let me have a limit, like this is your plus V naught sat line. Okay, plus V naught sat line, maximum output. And similarly, let me have a minus V naught sat voltage, minus V naught sat voltage. All right, now let me start from this point. At this point my input is 0. See, this is at origin, right? My input is 0. Okay, now as my input starts increasing in this positive direction, as my input starts increasing in positive direction, right side, so my output will remain where? Here. So you may be thinking, for positive input increase, why I am showing positive output? It is because it is my previous state. My output of op amp is positive because before increasing in positive direction, your input was in negative direction. It is like this. If this is your input, before increasing in positive direction, where it was? It was here, right? It was in negative. So for this portion of input, what will be the output? The output will be positive, right? So I am showing positive output. And how long your output will remain positive? See here. Even though my input is increasing from 0, my output is still at positive. How long it will remain positive? Till my input reaches UTP. The moment input reaches UTP, output will shift from positive to negative. Output will shift from positive to negative. So this point is our UTP voltage. UTP voltage means when my input increases, see here, it may be like 1 volt, 1 volt, 2 volt, 3 volt, 4 volt, 5 volt, 6 volt, like this. If UTP is equal to 4 volt now here, the moment it reaches, when the moment input reaches UTP voltage, output will shift from positive and comes to negative extreme, like this. Understanding? Okay. Now you have reached here. If you see input after input reaching UTP, further the input is rising. Can you see? Input is still rising, positively increasing. So where your output will be? Your output will remain in positive direction. Even if your input increases after UTP, your output will remain at minus V naught sat. Understood? Output will remain at minus V naught sat. Further what happens? Your input starts decreasing. It crosses zero line. Then input goes negative, right? The input goes negative. What about output? Output is still at minus V naught sat. So I can show it here like this. When input increases, then it starts decreasing. It is this. Further it will increase. Then when it starts decreasing, this portion, your output will still remain at this point. Okay. See, you came like this, downward. Then you will go like this for this duration. Your output will still remain at negative V naught sat. Then further your input will decrease till it reaches zero line. Then it will go like this. Understanding? Then your input will negatively increase. See, increasing, right? So you are going like this. Right? Further your input will starts decreasing and reaches zero line again. Right? It reaches zero line, increasing, decreasing like this. After crossing zero also, your output will not change. Negative direction over, now positive direction, it will increase. When it reaches UTP, once again I will come to this. This portion is done. Right? Yeah. When you reach this point, when you reach LTP point of your input voltage, your output will shift from negative V naught sat and goes to plus V naught sat. I repeat, when your input reaches LTP, your output will shift from minus V naught sat to plus V naught sat. It means your input, when it reaches LTP voltage, your output will shift from minus V naught sat to plus V naught sat. Okay? Plus V naught sat. So this is what we call it as input output characteristics. Okay? So there is one more name for this. We also call this as hysteresis curve. Also known as hysteresis curve. So this is how it is. Similarly, you can have the same topic with inverting Schmitt trigger circuit also. So let me prepare another video for that. So till then, thank you. Okay, let me stop here. Let us solve one problem on inverting Schmitt trigger. Okay, so let me write question first. Yes, I am done with writing question. So using 741 op amp with supply voltage of plus or minus 12 volt means VCC 12, design a inverting Schmitt trigger circuit to have triggering points plus or minus 2 volt. Triggering points plus or minus 2 means UTP equal to LTP. That is UTP is equal to 2 volt and LTP is minus 2 volt. Alright. Another thing, V0 will be how much? If VCC is 12, V0 will be VCC minus 1, that is 11 volts. Alright. So better you draw op amp in inverting Schmitt trigger circuit. Minus is been given as input, right? This is your positive, right? This was R1, this was R2, this is your V0, right? What all to find? Yeah, our trigger voltage is plus or minus 2 volt, that is UTP and LTP. So R2 is equal to trigger voltage divided by I2 current. So trigger voltage you take 2, I2 is 100 times of IB max, that is 100 into 500 nano amps. So this will give you R2 equal to 40 kilo ohms. Simple, right? Then what is remaining? R1. So R1 you have to calculate like this: V0 minus triggering voltage, right? Trigger voltage by I2, that is 11 volts minus 2 volt divided by I2. I2 is once again same 100 into 500 times of IB max. This is your R1. So this will give you R1 equal to 180 kilo ohm. 180 kilo ohm, right? Standard value. This is how you need to solve this. Thank you.